Okay, let's unpack this. We are diving into a figure who is maybe one of the most overlooked and yet, well, most profoundly influential scientists of the last 150 years, Sir Jagadish Chandra Bose.
That's right. Born in 1858, his life is just this radical intersection of physics, botany, and, institutional rebellion.
It's unbelievable. I mean, imagine a single person who pioneered technology that's foundational to modern Wi-Fi.
And at the same time, developed the earliest solid-state semiconductor devices.
And then on top of that, built these ultra-sensitive instruments to prove that plants experience electrical responses, almost like human nerve tissue.
What's so fascinating here is that incredible breadth, but it's coupled with this rare, almost stubborn refusal to monetize his genius.
Right.
He wasn't just a scientist. He was, I think, a true polymath who fundamentally rejected the artificial barriers of his era.
Whether they were disciplinary boundaries, separating physics from biology.
Or social barriers, like the colonial era racial discrimination he faced every day. His work, it really forces us to ask, what truly separates the living from the non-living?
Well, our sources today give us a rich, detailed look at Bose's journey. We're going to cover his revolutionary work in millimeter wave optics, the frustrating but essential controversy around his inventions.
And then his just astonishing discoveries proving the electrical sentience of plants.
So we're on a deep dive mission to understand the full scope of this genius who truly connected the living and the non-living. To really understand the universal scope of Bose's science, you first have to understand the philosophy he developed right from his earliest education.
You absolutely do. It starts in what was then the Bengal Presidency, modern-day Bangladesh. He was born in Mymensingh in 1858.
To a prominent Bengali Kayasta family. But the key context, as our sources point out, is that his family were part of the Brahmo Samaj movement.
And that background is, well, it's absolutely essential to understanding his lifelong fight against discrimination. The Brahmo Samaj was a reformist Hindu movement.
What does that mean exactly, a reformist movement at that time?
It was dedicated to modernizing, to questioning dogma, and, critically, to rejecting the rigidity of the caste system. Bose's father was a high-ranking civil servant, and he was deeply influenced by this progressive mindset.
And this mindset led to a very deliberate decision about Bose's education. His father just rejected the prevalent aristocratic status symbol of immediately sending your kids to expensive English language schools.
He did. Instead, Bose was sent to a local Bengali language school first.
A vernacular school.
A vernacular school.
Okay.
And this decision, it profoundly shaped his entire worldview. In that school, he was sharing his bench with children from every social stratum.
The son of a Muslim attendant? The son of a fisherman?
Exactly. There were no social hierarchies in that classroom. And he talked about this later in life at the Big Crampore Conference in 1915.
Right. He said he was spellbound by their stories.
Yes, these simple, profound stories his playmates told, they weren't about, politics or social climbing. There were stories about nature, about birds, animals, aquatic creatures.
And he directly credited that environment with cultivating this really intense, keen interest in how nature works.
And crucially, with instilling a lifelong rejection of caste or community discrimination. This wasn't just some abstract philosophy for him. It was a lived experience.
So when he eventually did enter the more orthodox world of higher education, he was already carrying that egalitarian view with him.
He was. He went to the Hare School in Kolkata and then St. Xavier's College, where the Jesuit father Eugene Lafont really fostered his innate curiosity in the natural sciences. That set his formal path.
But that path took a little bit of a detour, didn't it? He went to England.
A slight but very significant detour. He enrolled in medicine in London, but he had to quit. He had chronic ill health. And the thinking is it was possibly from chemical exposure in the dissection rooms.
And this turned out to be one of those, beneficial failures.
Completely.
Yeah.
Because it forced him to choose between the civil service, which was the prestigious, expected path, and pure scholarship.
And he wanted to follow his father into the Indian civil service. But his father actually forbade it.
He did. His father decreed that Bose should be a scholar who would rule nobody but himself. A powerful statement.
It really is.
And that set him on the course toward Christ's College, Cambridge, where he studied natural sciences. His advisor was the esteemed Lord Rayleigh.
A Nobel laureate.
A Nobel laureate known for his incredibly fastidious experimental methods. So Bose got degrees from Cambridge and University College London, trained by giants like James Dewar.
So you have this combination of extremely high caliber, state-of-the-art Western scientific training.
Coupled with these deeply progressive, anti-discriminatory Bengali roots, it just created this, well, this truly combustible personality who was ready to challenge the system.
And that challenge started, what, almost immediately upon his return to India in 1885.
Instantly. He was appointed as an officiating professor of physics at Presidency College, Calcutta. But the historical record is clear. The college principal and the director of education were very hesitant.
Because those positions in the Imperial Education Service were pretty much reserved for Europeans.
The racial discrimination wasn't hidden. It was institutionalized policy. The standard rule was that an Indian professor was paid only 2/3 the salary of a European peer.
Okay, so that's already a huge injustice.
But then they compounded it. Because Bose's appointment was initially temporary, an officiating role, they unilaterally halved his pay again.
So wait, he's doing the exact same work, teaching a massive 26 hours a week.
26 hours.
Yes, his European colleagues, but he's getting 1/3 of their salary. That's just systemic injustice right there in the administration.
And this is where his Brahmo-influenced philosophy just collided head-on with that system, rather than quietly accept it or, lobby internally.
Which is what most people would have done.
Oh, absolutely. But he made this extraordinary, almost passive-aggressive stand that lasted for 1,095 days.
He refused to accept any salary for the first 3 years.
Not a penny. He just worked. He taught his classes, he did his research, and he treated his job as an honorary position until they recognized his true worth.
What an incredible personal sacrifice. How did he even support himself during that time?
Well, we don't have perfect financial records, but we know he had family support.
Yeah.
His focus was just absolute. He made this 3-year protest a silent referendum on the principle of equality itself.
His reasoning being that if his work was valuable, they'd have to pay him eventually.
Exactly. Or, if they fired him, that would also be a kind of victory because it would expose the system's inherent unfairness.
And his integrity, it eventually forced the administration's hand.
It did. After 3 years, his performance and his popularity with the students were just undeniable. His appointment was made permanent with retrospective effect.
Which means he got all 3 years of back pay in a single lump sum.
A remarkable, sustained victory against that bureaucracy.
But the institutional struggle didn't end there, did it? Even after the salary was sorted.
Not at all. Despite his success in the classroom, the college administration actively resisted his research. They argued it distracted him from his heavy teaching load.
So he was constantly struggling for funding, for equipment?
Constantly. He often had to use his own limited resources. And it's really important here to note the support he got from the social activist and Hindu nun, Sister Nivedita.
She helped fund his research.
She did, and that kept his scientific output alive during this period of intense institutional resistance, so that his foundational discoveries, the things we're about to talk about, they weren't built in some state-of-the-art government-funded lab.
They were built in a small room, fueled by personal savings and just radical determination. Okay, so let's move from those institutional battles to the scientific revolutions that came out of that small lab in Calcutta. We need to look at how Bose basically created the foundation for modern wireless communication, starting with inventable light.
Right, so by the mid-1890s, the world was electrified by the work of scientists like Oliver Lodge, who was demonstrating the transmission and detection of long radio waves.
And this immediately inspired Bose.
It did, but he wanted to move beyond just simple detection. He wanted to start studying the optical properties of these electromagnetic waves.
Like light, how it reflects, refracts, polarizes.
Exactly. But to properly examine things like polarization and reflection in radio waves, you need wavelengths that are much, much shorter than the standard long waves being used for telegraphy.
So his whole goal was to make radio waves behave like light. And to do that, he had to miniaturize them.
Precisely. And his major breakthrough, and this is where his just staggering technical foresight comes in, was successfully reducing the waves down to the millimeter level.
Specifically around 5 millimeter wavelength.
Yes, which is firmly in the microwave range.
Yeah.
He was operating at frequencies as high as 60 gigahertz. To put that in context for you.
That's 60 billion cycles per second?
In the 1890s. It's almost unbelievable.
So to send a signal at 60 gigahertz and have it travel, 75 feet through 2 walls, he must have faced an immense technical challenge. What was harder, creating a powerful enough transmitter or a sensitive enough detector?
Both were monumental challenges, especially with the tools he had available in 19th century India. But the transmission side was perhaps the most demanding, just in terms of sheer precision.
Because at 5 millimeters, everything has to be perfectly scaled down.
Perfectly. I mean, the list of specific components Bose invented just to handle this frequency range, it reads like a modern microwave engineering textbook.
Okay, so let's list some of those. What did he actually invent?
All right, he invented the waveguide.
Which is basically plumbing for invisible light, right? A tube to guide the waves.
That's a great way to put it. He developed horn antennas to efficiently transmit and receive the energy. He created dielectric lenses, which are prisms made of materials like sulfur or pitch, to focus the waves, just like optical lenses focus visible light.
And he also created polarizers.
Various polarizers, yes. And critically, he was the first to use a primitive semiconductor junction for detection.
I want to pause on the foresight there because the sources are really clear on this. After Bose's initial success with these millimeter wavelengths, further work in this range was, virtually non-existent for the next 50 years.
50. He was operating in a technology space that wouldn't become practical for things like radar and satellite communication until the 1940s and 50s.
That gap just underscores his genius. He literally built a working 60 gigahertz system decades before the infrastructure or the materials science or even the institutional support existed to pursue it.
Right, and for context, much of his original equipment, which is still housed at the Bose Institute in Kolkata, would look instantly recognizable to a modern electrical engineer working on 5G or satellite communications today.
The fact that concepts from his 1897 papers are directly incorporated into receivers on modern radio telescopes today, that really confirms his foundational status.
It absolutely does.
The science was profound, but Bose knew how to make it visible. He was great at converting this cutting-edge physics into spectacular public theater.
He really was. In November 1895, at the Town Hall of Kolkata, he put on this vivid public demonstration of his millimeter-range microwaves.
And this demonstration was designed to silence the critics, the people who doubted that invisible light could actually penetrate solid objects.
Precisely. He transmitted his waves over a substantial distance, 23 meters, about 75 feet, and made them pass through two intervening walls of the hall.
And what happened on the receiving end? What was the payoff?
The waves were received by an apparatus that immediately did two very visible things. It rang a bell, and for the dramatic finale, it ignited gunpowder in a closed room.
So this wasn't just detection, it was wireless controlled signaling that defied physical barriers.
It was. The Englishman newspaper, which covered the event in 1896, they were so stunned they speculated his work could revolutionize the entire system of coast gliding.
And then there was that moment, that theatrical moment, when the waves passed through the body of Lieutenant Governor Sir William Mackenzie.
A superb rhetorical and physical demonstration. It showed properties that were just utterly alien to the public at the time, this idea of waves passing right through human tissue.
But beyond these dramatic shows, he was also pioneering these deep theoretical conceptual leaps, which brings us to his 1898 experiment using a twisted jute structure.
Yes.
This sounds incredibly low-tech compared to his high-frequency transmitters. What was he trying to do with twisted jute?
He was studying how waves behaved when passing through complex media, specifically the optical rotation of microwaves. He was exploring the properties of what we now call chiral media.
Chirality, so that's like handedness.
Exactly, like your right hand can't perfectly overlay your left. A chiral structure interacts differently with waves depending on their polarization and direction.
So by twisting jute fibers, he was creating a material with a very specific engineered internal structure.
He was using plant fibers to construct this intricate, repeating geometric pattern, a synthetic crystal, essentially. And this seemingly simple experiment was a foundational step toward understanding and engineering metamaterials.
Metamaterials, which are these engineered substances designed to have properties not found in nature, like bending light around an object, the things you hear about with cloaking devices.
That's the futuristic application, yes. Bose was designing structures at the millimeter scale to control the propagation of electromagnetic waves based on the material's geometry, not just its chemical composition.
It's an incredible conceptual leap. He's connecting material physics directly to the most futuristic concepts in modern wave science.
A century ahead of his time.
As groundbreaking as his pure physics was, his next invention immediately threw him into this massive commercial and industrial race for wireless communication.
A race he personally had zero interest in winning.
Right. So let's get into Bose's diode detector and his philosophical stance toward invention.
So Bose needed a reliable way to detect his short radio waves, something much more consistent than the crude spark gaps and early detectors others were using. In 1899, he announced his development of the self-recovering mercury coherer.
Okay, let's break that down for the listener. First, what is a coherer and why did it need to be self-recovering?
A coherer, historically, was the key receiver in early radio. It was usually just a small glass tube with loose metal filings in it. Normally, these filings have high electrical resistance.
Okay.
When a radio wave hits them, the filings cohere, they stick together,
Yeah.
and the resistance suddenly drops dramatically. That drop signals that you've received a wave.
So what's the problem?
The problem is once they cohered, they stayed stuck. You had to physically tap the tube. There was usually a little automated hammer to decohere the filings and reset the resistance to get it ready for the next signal.
So that manual tapping limited the speed of transmission.
Massively. And Bose's innovation was the self-recovering mercury coherer. He replaced the metal filings with a tiny, very delicate arrangement of iron, mercury, and sometimes carbon contacts.
And how did that work?
When the wave hit, the conductivity would briefly increase, but the surface tension of the mercury would naturally pull the contacts apart almost instantly, resetting the device without any mechanical tapping.
So that speed and efficiency made it revolutionary for continuous signal reception.
It was. And furthermore, this device was later recognized as the first patented solid-state diode detector. He filed for a British patent in 1901 and a U.S. patent in 1904.
But the truly staggering aspect of this is his simultaneous use of a galena crystal lead sulfide as a detector.
Right.
Why is the galena crystal so important in this story?
Because Bose was the first person to use a naturally occurring semiconductor junction, a mineral, to detect radio waves. Before this, detection relied on these metal filing devices or on vacuum tubes. The crystal detector is the direct, lineal ancestor of every modern semiconductor device.
The transistor, the microchip.
The entire foundation of modern computing and communication.
Which brings to mind that quote from the Nobel Laureate Sir Nevill Mott that we found in our sources.
Oh, it's a great one.
He said, J.C. Bose was at least 60 years ahead of his time. In fact, he had anticipated the existence of P-type and N-type semiconductors.
And that's not hyperbole. It's a technical acknowledgement of his priority. He understood that certain materials, like galena, had these properties that made them better wave rectifiers than traditional conductors. He was intuitively working with the principles of semiconductor physics decades before the field was even formalized.
But despite holding the key to the future of communication, the sources all highlight his profound disinterest in commercializing any of it.
And this connects directly back to that philosophy we talked about in the first segment. Bose viewed his research as being focused on the nature of the phenomena, a universal truth to be shared.
Unlike Marconi.
Right. Unlike Guglielmo Marconi, who was aggressively pursuing commercial dominance, Bose just preferred to lecture and publish his findings openly. A friend in the U.S. did persuade him to file a patent on his detector, but Bose just allowed that U.S. patent to lapse. He wasn't interested. He basically offered the technology to the world for free.
And that lack of commercial drive is exactly what led to one of the biggest attribution disputes in early radio history.
It sets the stage perfectly for the Italian Navy coherer scandal.
Marconi needed a highly sensitive, reliable detector for his big transatlantic wireless transmission attempt.
He did. And Marconi's success in receiving the Morse code letter S on December 12, 1901, at Signal Hill, Newfoundland, it was a landmark moment. But the device he used to receive that signal was heavily influenced by Bose's work.
It was a modified version of Bose's self-recovering detector, the iron-mercury-iron setup.
Yes, or iron-mercury-carbon. That was the core of it.
So how did Marconi get his hands on this specific design?
In mid-1901, he got the design through Lieutenant Luigi Solari of the Royal Italian Navy. Solari's modification was just to encase the mercury droplet between the electrodes inside a sealed glass tube, which made it more robust for field use. Marconi then filed his own patent on this modified device.
And the controversy, the Italian Navy coherer scandal, it erupted in 1902. When claims emerged that Marconi wasn't the originator, priority was suddenly attributed to other people.
All sorts of other people. A naval signalman named Paolo Castelli, a Professor Tommaso Tomasina, who had also experimented with mercury-based coherers.
And this is where the detailed historical analysis, especially from organizations like the IAEE, really provides the necessary clarification. It establishes Bose's priority.
Yes, because the crucial element wasn't just using mercury, it was the design implementation.
What was the specific technical distinction that proved Bose's priority over someone like Tomasina?
It was the integration with a telephone receiver. Bose's 1899 design was built for continuous auditory detection. You could listen to the signal.
Which you would need for his high-frequency waves.
You'd have to have it. And the historical records confirm that Thomasina's earlier, simpler mercury experiments, they lacked this crucial telephone integration. So it was Bose's combination of the self-recovering high-speed contact with the continuous auditory output that provided the sensitivity Marconi needed. That's what made his design the technical ancestor of the device that heard the S cross the Atlantic.
And Marconi, citing commercial secrecy, just omitted references to Bose in his accounts. He focused on Solari's modification.
And that omission, coupled with Bose's own indifference to patenting, allowed the history to be obscured for nearly a century.
It really raises an important question, doesn't it? How often does the sheer gravitational pull of commercial success just overshadow fundamental non-commercial scientific discovery?
I think about that a lot. Bose allowed his technology to become a global public good. And in doing so, he allowed others to achieve fame and fortune based on his core technical leap. His reward wasn't wealth, but the pure satisfaction of understanding the phenomenon.
So now, we cross this incredible intellectual divide. After pioneering the physics of invisible light and semiconductors, Bose just pivots entirely.
To biology, specifically botanical responses. He took the same rigor and electrical precision he applied to 60 gigahertz waves, and he applied it to a leaf.
It's an amazing shift. His transition was motivated by a core hypothesis, right? That the principles of response were universal.
That was his driving idea. His major contribution to biophysics was demonstrating that the conduction of stimuli in plants, things like a physical injury, heat, chemical agents, that it was primarily electrical in nature.
Not purely chemical, which was the prevailing theory.
Exactly. He argued it was electrical, and that it behaved in a manner parallel to animal nerve tissues.
So the botanical community at the time, they largely believed plant reactions were these slow, purely chemical processes, and Bose essentially looked at a plant and said, I bet it has a nervous system too.
And to prove it, he had to create instruments of just unheard of sensitivity. This is where we introduce the crescograph.
His ingenious invention. The sources describe it as an automatic recorder capable of registering extremely slight movements. But how did he get it sensitive enough to register these tiny changes in plant growth?
Well, the mechanism was just a brilliant piece of mechanical and optical engineering. It combined a very fine system of levers with a clockwork mechanism, which recorded the plant's movement onto a smoked glass plate.
But the key was the magnification.
The key was the magnification. The system had a tiny gear train and used optical magnification, so it was capable of registering movements as small as 1/100,000th of an inch. By compounding mechanical magnification with projection, the crescograph could effectively magnify a plant's minute movement up to 10,000 times.
10,000 times. So if a plant grew 1 millimeter, the recorder would register 10 meters. That's the level of sensitivity that allowed him to capture these instantaneous responses that were previously completely invisible.
That speed and sensitivity let him measure plant response to stimuli with the precision of a physicist measuring an electrical current.
And he focused on plants that were known for movement, like the sensitive plant Mimosa pudica.
The one that famously folds its leaves when you touch it. And also the telegraph plant, Desmodium gyrans, whose tiny side leaflets are constantly twitching.
And the results he got were revolutionary. He used the crescograph to generate these electrical readings, showing a direct, immediate response to injury or stimulus.
Exactly. He was documenting the electrical nature of these responses. Essentially, he was measuring action potentials.
Electrical spikes, like the ones generated by an animal nerve or muscle fiber.
The very same phenomenon. He recorded the quivering of injured plants, which he interpreted as a measurable physiological response akin to pain or shock in animal tissue.
So, just to be clear, what is an action potential in this context?
Think of it as a sudden, rapid, temporary change in the voltage across a cell membrane. It's a rapid firing of an electrical signal. In animal biology, this is how nerves communicate.
And Bose was recording this exact electrical phenomenon in plants.
He was. He argued that an injury or a stimulus caused ion channels in the plant cells to open, generating an electrical pulse that traveled through the plant tissue, similar to an animal impulse, just much slower.
And his research went beyond just injury. He studied seasonal effects, the action of microwaves on plant tissues,
And how plants move toward light heliotropism. His work on that is a beautiful example of detailed measurement. He invented a torsional recorder to study it.
And what did she find?
He found that when light was applied to one side of a sunflower, It caused turgor, that's the internal water pressure that defines cell rigidity, to increase on the opposite side.
Which is what pushed the stem toward the light source.
Exactly. He was mapping the physics of movement within plant life, revealing this highly sophisticated system of hydraulic and electrical control.
And his measurements of electrical response in plants, they allowed him to make an even bolder claim, a philosophical and scientific claim, that blurred the line between biology and physics entirely.
Yes, in what he called the metal cell analogy.
Right. So Bose believed that fundamental physical laws governed all matter. If living matter responded with an electrical curve of fatigue and recovery,
Why shouldn't non-living matter subjected to similar stresses? So he performed a comparative study of the fatigue response of various metals and organic tissue in plants.
so he's taking metals like iron and subjecting them to mechanical stress, heat stress, electrical stress. What similarities did he actually find?
He noted these striking, quantifiable similarities in the cyclical fatigue and recovery response. If you repeatedly stimulate a muscle, it tires, and the electrical response weakens. Given time, it recovers.
Yeah.
Bose found that if he repeatedly sent electrical pulses through a metal wire, the metal's characteristic electrical response curve, its change in resistance, would also weaken. It showed fatigue, and given time, it would recover its initial responsiveness.
I understand the measurement of fatigue in metal, but how did he justify that leap scientifically to the skeptics? I mean, that seems to negate the difference between a machine and a life form.
But that was the entire point of his 1902 book, Response in the Living and Non-Living. He argued that what we traditionally define as response or irritability is merely a physical characteristic that's measurable through electrical language. The differences are of degree, not of kind.
And the most profound part of this analogy involved his use of poison and anesthetics.
That's the part that's truly mind-bending. He demonstrated that when anesthetics like chloroform were applied to plant cells, the characteristic electrical response curve to a stimulus would decrease and eventually just disappear.
Just like an animal losing consciousness.
Precisely. The same thing happened when he applied poison. The cells just ceased to react electrically.
But the kicker, the true moment of blurring that line, came when he treated metals with chemical agents.
Yes, he observed the same exact response when applying specific chemical agents to metals. When he treated metals with, for instance, oxalic acid, the metal's ability to exhibit its characteristic electrical response curve was suppressed or eliminated.
So he was using the language of biology anesthesia, poison, fatigue, recovery to describe physical changes in a piece of inert metal, and vice versa.
Here's where it gets really interesting. He essentially treated a piece of metal like a nerve cell, and a nerve cell like an electrochemical device. He was blurring the boundaries using the universal language of electrical response.
And his conclusion was that the electrical impulse was a universal characteristic of all matter.
Which was a radical science that went completely against the dominant Western mechanistic views of life. It's important to remember this wasn't just a metaphor for him. He was measuring precise, quantifiable electrical changes. For Bose, the transition from the non-living to the living was not a sudden chasm, but a gradual slope governed by the same set of physical laws.
It's clear that Bose was driven by something much larger than just personal recognition or even specific scientific fields. He was driven by a commitment to experimental science in India.
Absolutely. Which brings us to his legacy as an institution builder.
He understood that for science to flourish in India, it required dedicated interdisciplinary infrastructure, free from the bureaucratic and colonial restrictions he had been fighting his entire life.
So in 1917, he established the Bose Institute in Kolkata, and he served as its director for 2 decades until his death.
And our sources note that this was Asia's first interdisciplinary research center, built specifically to study the unity of physics and biology. What was the underlying statement he was making by founding this institute?
It was a direct challenge to that colonial-era belief that the Indian mind was only suited for, theoretical or metaphysical speculation, and would shy away from rigorous experimental science.
His inaugural dedication was incredibly powerful. He called it not merely a laboratory, but a temple.
A temple dedicated to nature. He declared, I'm quoting here, "It is not for man to complain of circumstances, but bravely to accept, to confront, and to dominate them. And we belong to that race which has accomplished great things with simple means."
He was offering a space where research could be pursued at the highest level, proving the capability of the Indian scientific mind. This institution was a crucial national statement of scientific sovereignty.
Yes.
And his literary output during this period was also pretty prolific. Beyond his huge scientific texts like Response in the Living and Non-Living and the Nervous Mechanism of Plants, he also branched into fiction.
He did. In 1896, he wrote Nirodashur Kahini, which means the story of the missing one. He later expanded it into Palatak Tufan, or Runaway Sea Storm,
And this work is recognized as the first example of Bengali science fiction.
the father of Bengali sci-fi. He was speculating about the future implications of science, things like weather control and natural disasters, even as he was inventing the present. It just shows this holistic mind that sought not just to analyze the world, but to imagine its potential.
Despite the controversies over attribution, the honors did start to accumulate, especially later in his life, solidifying his status as a major global scientist.
They did. His recognition included Companion of the Order of the Indian Empire in 1903. He was made a Knight Bachelor in 1917, and in 1920, he was named a Fellow of the Royal Society, the highest accolades of the time.
But the most important recognition often comes decades later, doesn't it, when the historical record finally it's corrected.
That's often the case.
And his experimental work in millimeter band radio was recognized in 2012 as an IE milestone in electrical and computer engineering.
Which was the first such designation granted in India.
Yeah.
And that IE milestone is incredibly significant because it confirms, through rigorous technical analysis, his priority in the development of microwave technology and the crystal detector.
He's also received a lot of cultural legacy markers. A Google Doodle in 2016, a crater on the moon is named in his honor.
And there's that fascinating tidbit from 2018 where he was on the nomination list for the redesign of the UK 50-pound note for his work enabling Wi-Fi development.
It just illustrates his belated but powerful recognition as a key father of modern wireless communication.
And finally, you have to return to his core philosophical view. It underpins everything. It explains why he fought the system on salary, but gave away his technology for free.
He drew inspiration from the epic Mahabharata, specifically the figure of Karna.
Yes, valuing the higher and higher idea of conflict and defeat. He said that worldly success often seems small compared to the true success born of defeat.
What a perspective.
His core belief was that the only real lasting advantage is to fight fair, never to take crooked ways, but keep to the straight path, whatever be in the way. This integrity just perfectly explains his decision to forego patents and commercial gain.
His victory was internal.
It was, establishing truth through rigorous experimentation, not external wealth or fame. He knew that even if others took the immediate credit for the coherer, the truth of his fundamental discovery would eventually stand on its own.
What an incredible journey through a life that just defied categorization. Sir Jagadish Chandra Bose was the physicist who took radio waves to 60 gigahertz.
The engineer who fathered the crystal radio detector.
The biophysicist who made plants speak through electrical response, and the visionary who founded Asia's first interdisciplinary research center.
You know, if we connect this to the bigger picture, Bose demonstrated that a true scientist operates without artificial barriers. He moves seamlessly from material science and electromagnetism to plant physiology,
Forcing us to fundamentally reconsider what we define as life and response.
His work showed that universal physical laws govern reaction across the entire spectrum of matter, from a piece of metal to a sensitive plant leaf.
So what does this all mean for you, the learner? It means the seamless wireless communication you rely on every single day, powering your phone and your Wi-Fi, has deep, forgotten roots.
Roots in the hands of a dedicated scholar in Calcutta in the 1890s who refused to compromise his principles.
And it means that the plant life around you is far more electrically responsive, far more sensitive and interconnected with the physical world than you likely ever imagined.
His legacy isn't just his inventions, it's his ethics. He valued scientific principle and integrity over profit and patent protection.
Bose believed in fighting fair and accepting defeat as a pathway to true success. So given his experience with the coherer controversy, where his technical priority was established decades after the commercial success of others, what contemporary scientific field currently battling for recognition or against overwhelming commercial pressure might hold a Bose-like revelation that history is only just starting to acknowledge?
Something to think about.
Something to think about as you connect wirelessly and maybe, look a little more closely at the nearest houseplant.